Okay, so now you should see the actual screen without the notes.
Yes.
Very good. So I titled my talk "Humans in Their Spatial Context." Basically, I thought of sort of combining my own two research interests, which is eye tracking and extended reality, because the word spatial computing is used by the extended reality community as such. One of the key quotes that I sort of wanted to share with you is that eye tracking has important implications for virtual experiences. This, I think many of you intuitively can imagine, but let's have a look at a couple of the examples. Of course, being able to track the eyes and being able to track the entire world, including the body and the environment and basically real-time mapping of the environment, it gives us an interesting shift in the way that we map things before. So spatial computing is used by the extended reality community a bit differently than the geography community. So if you go to geography, most of the time, spatial computing pops up in statistics papers. But in modern extended reality literature, that basically means that the device can map its surroundings in real time. So it can become aware, ideally even semantically, be able to control and say that this is a table and this is a door and this is actually grass and so on and so forth. Many of these devices can already do that. This is computationally extremely heavy, but it is getting more or less there. And many of them also come equipped with eye tracking. When I talk about eye tracking and extended reality, it's still a sort of a work in progress. You can, as many of you know, it's not so common. I don't have eye tracking in my phone or in my webcam right now, or I'm still using a projection display rather than an extended reality display to talk to you. So things are kind of at the edge of the technology, if you like. It's not exactly mature technology, is not yet. But it's getting better. And one of the things that we've done, sorry, my alarm tells me to log in. It was supposed to be, sorry, I'm just a little bit throaty as well, so I needed to sip something. So we have done something, for example, using an external webcam recently with a master's student to track the gestures. And this has, because of the machine learning, this is ordinary webcam. It doesn't have an active camera. It's not a depth camera. It doesn't have time of flight. It basically can track the gestures and recognize covering that there's no human, there's no gesture, that somebody's shrugging shoulders or raising their hand and so on and so forth. So this was done to support a virtual camera where somebody was virtual reality headset where somebody was wearing a headset and they have internal camera, and it already enables detecting certain gestures. And then we have added an external webcam for which you can then track the partner's movements. Similarly, smartphone eye tracking is getting there. So you have, for example, someone else's paper. This is one of my master's students, but this is from a team from Google. They have offered a publication. They compared a smartphone-based eye tracking system. Of course, all of this is all machine learning related, right? So you can. This is why you can do it. Previously, eye tracking was not exactly possible with the smartphones, but now it is more and more possible because we can basically benchmark the whole thing using machine learning. And their accuracy using smartphone algorithm actually came pretty close to Toby in terms of error rates, which, you know, it costs 30,000 francs or whatever to buy. And we tried it also on ourselves in the smartphone context. Excuse me, I'm hearing some echo. Okay. Did you guys change something? Okay, it's better already. Okay, thank you. All right, and then I wanted to go back again to extended reality and tell you why does that matter in terms of, let's say, geography or geographic information science. It is an inherently spatial domain. It tries to replicate real world feeling of space and place, and it computes space. It does real-time surveying, if you like, and relies on spatial registration. So that's a key method. It essentially georeferences everything, and it overlays attribute data on real or virtual spaces. And I would say from that perspective, it has some parallels to GIS. Combines analytical and experiential approaches in one, which is then the immersive analytics. And it is something that I think it's really matters for spatial sciences. You could say that there are some extended reality applications that are non-geographic. Obviously there are, but it's hard to argue if there's an XR that is non-spatial. What is with this georeferencing part, I think this audience might already know that, but I wanted to quick refresher of the recent non-clementure about augmented reality versus mixed reality. If you take augmented reality is not as computationally expensive these days, the way that at least the modern definitions of it is, because if you go back to the old definitions, it's kind of the other way around. It's quite confusing literature. But if you display just a bit of information anywhere in the world, then that's considered augmented reality. But if you actually show the stuff in spatial context, it is considered mixed reality. At least that's what Microsoft is pushing. And since Microsoft is pushing, a lot of people are adopting this definition. So that would be a virtual cat floating anywhere, augmented reality. But if the cat sleeps on the chair, cat is virtual, chair is real, then you have actually mixed reality. And spatial computing, therefore, is real-time mapping of the space using, I would call, photogrammetry or computer vision. The two are getting harder to distinguish. Excuse me. So some examples from our work. So I wanted to this is kind of a list of my projects. These are mostly my past projects. A lot of them have eye tracking in it, and the new ones, many of them have virtual reality in it. And today I'll talk to you a little bit on the collaborative mixed reality. I will not walk through the list because it's kind of a long one. Just the main message was that I've done many projects about eye tracking, and I'm doing many projects that are to do with extended reality. And I'll show you a couple of examples from these. For example, one of the cases I found it inspiring, a student project. They took some photographs from 1900s from Zurich main station, and then you can basically point your phone and see the historical events or some gamified stories in its spatial context. So all of a sudden, your environment that you're standing in looks like what it looked like in 1900s. And then you go through, there was a whole implementation of a game here. And another implementation from one of the master's students on our side was sort of, I would say, very geospatial. She was digitizing a museum entry database from this kind of text into some sort of geographic representation that you could browse within virtual reality. So all these things are somewhere in Switzerland in a museum, but they originate from elsewhere. So she would put them in their geographic origins and try to also address how uncertainty should be expressed. And then you could go to the object and learn more instead of looking at a page like this. She found that there's some hedonistic qualities. This one I didn't mention generated a very strong engagement. There's a scale called user engagement scale. And this was, as you can see, very tidily packed into the very high corner, which is, I would say, basically not surprising, but it's nice to see. And then two other things I basically wanted to let you know, because advertising the student work here, Ian recently has done some immersive mental rotations test, evaluating spatial ability in virtual reality. This is mental rotations test. You might have heard before. It's a standardized test to measure somebody's mental rotation ability. It's used by psychologists. And in this one, basically, if you put the rotation in its spatial context, if you like, and make it more like what you would experience in virtual reality, he wondered if the findings would be stable. So you would have the 2D and then you would have the 3D ones. And it is quite interesting. It replicates some findings from some earlier work, but what is quite interesting here is that it actually reduces some gender differences that is usually found in this task. So this, I think it's a whole different talk. I'm just mentioning them in case anything resonates with you. Please talk to me. I'm happy to share the papers or explain them more. And here another, so this is kind of extended reality paper. This is again eye tracking paper. I go between the two back and forth quite a lot. And in this one, that was a visual saliency prediction, again, because machine learning enables us to do things differently, or, well, yes, differently is the good word, more precisely, quicker. Then we actually worked on a visual saliency prediction that is benchmarked against an eye movement data. So the algorithm tries to say what is visually salient in a scene, and then you benchmark this against an eye tracking data set where people are viewing the scene. All right. This is the one project where eye tracking and the extended reality comes together, a collaborative mixed reality project. And that is specifically for spatial decision making. So I'm going to tell you a little bit more on this one. So you could say that in terms of collaboration, our current models are video-based, like what we are doing right now. And the spatial phenomena is especially difficult to communicate or collaborate on. So if I have to hand it to something to you, or if I want to do a little bit of like what is behind, what is near, what is far. And XR offers a better sense of presence and then makes this spatial phenomena a little bit more accessible visually and cognitively. More interaction, more cooperation and equal participation than video conferencing, according to one study. So if you do the collaboration using mixed reality or virtual reality or extended reality in general, actually people tend to interact more and cooperate more, and more people participate. And they interact with the space and interact with each other in the same virtual space. And the question is, how do we interact with each other and with space? Do we do gestures or gaze or speech? So we explored a little bit of that. One thing that you do in collaborative mixed reality is a sort of a key concept is awareness cues. So you basically leave little crumbles of what your collaboration partner is doing, and somehow it's marked so that you actually become aware of what the partner is doing spatially, if we become spatially aware of it. And this, in many studies, have been shown to improve user performance, usability, and subjective preferences. This includes avatars, things like you can have the avatar of the other person. You could therefore have some sort of eye contact, which we are also working on. It sounds like it might actually end up being a little bit unsettling or creepy, but we will see. And then you can, of course, have gestures and body language. You can try to share the fields of view. So you could basically teleport somebody to someone else's seat. So ideally, right now, if there was a system like that, I could take a seat in the room that you guys are in. And this is what you can potentially enable. You can use pointers, gaze, speech, or actual annotations. So we experimented with gaze and annotations, and one pointer, I'll show you those. We have a number of collaborative extended reality projects. I'll just skip through it. One of them is about navigation. The other is about spatial planning and virtual labs for physics education. This is also collaborative because an education teacher and the student would have to be in the same room in one way or another. And here it's also quite interesting because we try to connect so the teachers in the VR environment, but the students are in their cell phones. we try to connect them together so they can still communicate with each other. And then we have a construction project within, it's a local school initiative. And then we have this collaborative MR project that I marked in the project list earlier. And here we have an INOSYS funding that has actually 3 external partners and 3 internal partners. The internal partners are ourselves. We are at the Institute of Interactive Technologies, School of Applied Psychology, and School of Design. And then you have a couple of 2 companies. There's a furniture company, that's an extended reality company, and there's Zurich City. And the goal for the city of Zurich is to have architectural bidding or architectural competitions. So you have a jury that receives proposed buildings, and they so far have been using paper models to discuss the proposed architectural changes, whether it's a train station or a regular building or a park. And now they want to move to a mixed reality setting. And then you have 11 people looking at this building at the same time, and then it gets quite quickly confusing. But it's useful from the perspective that they can actually see the proposed building in its neighborhood, because they can go out and walk and put the HoloLens and then see the building in its context. So in that sense, it is actually quite useful, but to be able to point at something in that and tell your friend why this is the better proposal, or tell your colleague why that's the better proposal and what is wrong with it, etc. So enabling discussion and collaboration becomes hard very quickly. So one thing that we thought might help is to enable some sort of a pointer, whether it's a gaze pointer or a handheld pointer. This is a gaze pointer scenario. I'll tell you more about this project. Or also have a digital twin of the physical object. If you are, for example, in the office and the other person is in the field, a digital twin of the field objects could be actually transposed or sent to the person sitting in the office. We also worked on avatars, but I'm not going to talk about this today. And that's the VR Labs example, where we have some solar energy calculations, and we have collaborative MR project, which I'm going to show in connection to these 2. All right. Yes, Marinos, am I talking too long?
No, go ahead, Arzu.
All right. Thank you. All right, so the pointer application basically tracks the hand. So you can have, this is a proposed building or a train station, new plan. And you can basically do that, and your partner would see this. You can display it as a line, you can display it as a point. You can also do the gaze visualization. You can see that the head is being tracked, and you can also see where they are looking. And even from her body posture, I would guess somewhere here, but it actually displaying makes it more precise. But of course, if you have multiple partners, this gets complicated very fast. And the other thing we experimented in this project, which I didn't mention earlier, is this little shared perspective idea. That you see this little tablet on this corner here that looks like a frame, gray frame. That is the viewpoint of the other party. So you have, I'm standing here, she's standing there, and I can see how the world looks to her. I find this interesting. So you can basically, at the moment, it's not really that you teleport yourself there, you still have your own view and you have the view of the other person. But it's also complicated because I think it requires quite a bit of mental rotation, but it's still quite enlightening to see how the view looks at the other person right at this moment. In this case, we basically have the virtual model. We brought it because it fits with the case study. We brought it and put it on a table, similar to a paper model. All right, so this is a little video. So you can, I just wanted to show you the gaze visualization part. So she can, in a few seconds, she will switch on the gaze. That's when she's toggling gaze. And that's the gaze visualization. As you can see, it's quite nervous and jittery. So that's not so easy to do it right. But it's there now. You can see two people, and you can see the pointer in a different color than gaze, so you can distinguish hand tracking from gaze tracking. You can also distinguish different individuals. You can label these, or you can make each individual a different color if you wanted to do it like this. But we played around this just to in the previous study. We played around this idea of whether we should show this line, whether we should show it as a dashed line, or a handheld pointer as a kind of a baseline. So you have a virtual pointer, or then you can show the gaze cursor as a disk or a dash disk or a circle or a square, just a few alternatives. And this was the digital twin part. So you had something physical on one side that was represented on the other side as a digital twin. And here we did the annotations. What we did is, these are highlighting basically. So each of these red lines and then these blue lines, they are virtual elements. And this is displayed on the digital twin on my side, but also displayed on the physical twin on the other side, because both parties are wearing HoloLenses. And this is a sort of a field technician scenario, because this was in collaboration with SBB, with the Swiss Federal Railways. So you can annotate the space to guide the attention. That's another awareness cue kind of thing. Basically, we did some pilot studies. This study is still ongoing, but what we observed was that, of course, it's not going to come to you as a surprise, but optimal solution depends on the role, context, and task. And the gaze apparently had a higher system usability scale score. This is only 6 people, but for usability studies, usually after 6 people, you don't detect new errors, so it can even mean something. Then virtual pointer and gaze line appears superior to automated gaze line. I didn't discuss automated gaze line properly, but we had a version of this line which disappeared if there was occlusions, and then it appeared again when there was no occlusions, which did not work well. This obviously was not a good concept. And yeah, people liked this stable gaze line solution most in this case. And then in the other study, we had 18 people in 9 pairs with the annotations. That was, I think, quite informative. When you added the annotations, the number of verbal interactions between the 2 parties was lower than if you had a video communication. So we had video communication as a baseline, and these theatic words, they are spatial words, basically near, far, up, down, and things like this. And this was also fewer when you had the digital twin or the annotations there. And task completion was slightly faster, and the expert noticed the errors made by the field technician more often. Here, the context was navigation, but here in this case, it's not. It's really like this is a control box. It's like a actual technician doing something in a construction site or so. And usability was fine with the digital twin case, but what was also interesting is that experts really liked the digital twin and annotated digital twin solution, while the technicians, those in the field, they actually prefer the remote assistant, which basically is a video communication that supports the HoloLens. It's the Microsoft's built-in collaboration tool. So what do we discuss? Of course, as with a pinch of salt, because these are pilot studies, optimal solutions do depend on the role, context, and task. That means like what is maybe a better solution for the expert may not be a better solution for the technical person. Or in this collaboration scenario, we could talk about maybe a person who's a recipient of the message and person who's actually trying to explain something. So the expert and technician doesn't have to be the exact professions. And awareness cues through annotations or gaze solutions both seem to have potential to improve certain things, but you have to do it right. And more experiments are needed, especially in our case with the 6 people. We don't have huge conclusive basically early experiences at this point. And then we have the dash line options didn't work too well. Perhaps the scene was fairly complex in this case, and the dash lines were not so easily visible. And yeah, the design, do not underestimate the design choices. This is also true for maps. You can't underestimate what a small amount of modification in the line thickness or a little color change might actually affect in terms of performance. All right, so we have an experiment ongoing with 45 people, and we also have an actual study coming out with the experts. These are very hard to get, but we have scheduled in October, we go and observe the jury using the HoloLens with some of our interventions and try to understand a little bit how it goes. This is hard. I mean, technologies are hard, but it's also hard to measure what is good collaboration. And for that, we are hoping our applied psychology partners will step in and actually give us exactly how to measure good collaboration. This, for example, number of verbal interaction, diegetic words, etc. They matter, but the collaboration also means trust and you know, the tasks are shared properly and things like that. All right. So if you zoom out a little bit from these individual examples, what opportunities lie in this is that we get a knowledge of the context, which we didn't have until recently using a mixed reality headset. This allows us to potentially better assess the user needs because we understand what they are surrounded with, or at least we get some information about what they are surrounded with, and then we can optimize maps. Of course, there's a lot of little things about technology that we can do, gaze control menus, we can do foveated rendering, personalization, eye contact, nonverbal cues, and so on and so forth. All of these are smaller technical things that one can show, but also there's an immense potential or countless potential for applications. There's phobia treatment, you can do virtual laboratories. I mean, CERN costs a lot of millions, but if you have a virtual CERN in which you can simulate things, of course, it's much cheaper. Even though it's not a simple thing to do, it is much cheaper, at least for educational reasons, one can do that. And yeah, and all kinds of other applications, training simulations or tourism. And challenges for eye tracking coupled with XR, you might have an uncanny valley effect. This is a known effect if you are not familiar with it. If something is realistic but not realistic enough, so it's like abstract feels fine, and then more realistic, somewhat more realistic, fine, and then it gets to a point where it's realistic but not realistic enough. Then it makes people uncomfortable. So eye contact might actually also lead to that. 3D eye tracking is still a bit of a work in progress. 2D works quite well, but 3D requires actually detecting accommodation. At the moment, we can detect convergence, but accommodation is not so easy. And virtual reality, in virtual reality, accommodation and convergence can be decoupled. This is a research problem, if you like. And of course, big data is still the problem. You can produce so many eye tracking data points in real time in combination with already computationally heavy environmental calculation. You may have some limitations there. And of course, the social issues. The big brother knows where you look, how long and how often. This has implications. If you have an obnoxious advertiser, it's a nightmare. Or there's actually a chance that someone actively controls what an individual sees, because if you have a glass, let's say if wearables or a chip is our future, I don't know, then if somebody hacks, they can make you see things that are not there. So there's all kinds of interesting issues here. Also, maybe some very fundamental issues about object permanence if children grow up with this. And then, maybe if we arrive at a point where we cannot tell real from virtual, things like deepfakes, it might lead to very strong misinformation. And of course, we have also risk for worsening all sociopolitical problems we already have, things like digital divide and privacy issues, and unwanted virtual litter, or other ethical considerations. Sorry, I don't know how I managed to do this format issue there. This was a paper that we wrote with a number of you probably in the room. I will not go through the list, but if you want to, you can have a look at the paper. The paper is Extended Reality in Spatial Sciences, a review of research challenges and future directions. So you can see there's a lot of people who contributed to that paper. And here we basically went through what might be actually good. I mean, many of what you see here are also here, but a little bit more in depth. So I'm going to leave you at this. Thank you very much. I'm leaving you with a provocative question of if cyber cartography is more or less what metaverse is. So thank you very much for your attention.
Thank you very much. So it was a very exciting presentation. I'm sure the audience enjoyed it, but they may have questions. It was so exciting. I didn't want to interrupt you, or it will change a bit our schedule for the rest of the morning. But the good thing is that you touched upon a number of things that we were ready to talk about in the second part of the workshop. So more or less, you answered quite a few questions of the ones we have to address later on. So before we move to the second presentation, are there any questions for Arzu? Please, we'll be happy to respond. No questions? Arzu, there are no questions.
Everything was clear, I guess.
Yeah, you did something right or wrong. Right. Okay, excellent. Oh no, there is a question. There is a question.
Maybe respond to Arzu's question. The cyber cartography versus metaverse. So it's very diverse. What do you think yourself? Of course, well, it's certainly possible to make equality between those two. But what do you think yourself? You have studied this so much.
Yeah, that's. I don't think the maps will go away. I think that there may be, I mean, because in some sense it's real-time mapping, there may be a lot of real-time annotations of the physical world and so on, but you need the overview. You need the overview for being able to see the context, and this first-person views are not sufficient for what the maps can fulfill. So I don't think metaverse is the sole answer. I think the maps, we will still need standard maps with aerial views. But it may be coupled, or it may be used less for navigation potentially. But of course, one can also say what is cyber cartography versus regular cartography, and then maybe cyber cartography fits more to the extended reality, and regular cartography is what stays. That part is also a little bit open from my side, so maybe someone else can help me better contextualize exactly how should we see the term cyber cartography. Marinos, maybe you.
Thank you. Well, thank you very much. Anyone else? Any other question? Well, if not, thank you, Arzu, again.
Thank you very much.